Section 7.7, Factoring Special Products. This is just a section that teaches us a couple of shortcuts to allow us to factor effectively without using one of the other methods. It's not always usable, but only in certain circumstances. Let's remember our special products from before. We had something called the difference of two squares, where we had a squared minus b squared that came from the multiplication a plus b, a minus b. We also had two different perfect square trinomials. We had a squared plus 2ab plus b squared, which was the result of a plus b squared, or a plus b times a plus b, and a squared minus 2ab plus b squared, which was the result of a minus b squared, or a minus b times a minus b. Basically, what we're going to try to do here is spot any time that we have a polynomial to be factored in one of these three formats: a squared minus b squared, a squared plus 2ab plus b squared, and a squared minus 2ab plus b squared. And if we have it in one of those three formats, we're going to quickly jump to the factored form. Let's see what this looks like in practice. We'll start with the difference of two squares, a squared minus b squared. This is going to happen anytime we have a binomial, two things, where the first part is a perfect square, the second part is a perfect square, and we have a subtraction. If I look at my first example here, x squared minus 25, I can write that so that it's something squared, x, minus something else squared, 5. Which means that it's written in this format up here, a squared minus b squared. I can now immediately jump to a plus b, a minus b, which in this case is going to be x plus 5, x minus 5. And that is the factored form of x squared minus 25. I don't need to use the Punnett square. I don't even really need to check it because it's a special case and I know it's going to work out. Let's try that with my second example. 4z squared can be written as something squared. It happens to just be 2z. 2z times 2z would be 4z squared. And 1, it's almost too obvious to spot sometimes, could be written as 1 squared. Once again, I have something squared minus something squared. I'm going to end up getting 2z plus 1, 2z minus 1. And that is my factored form. You can FOIL to double check, but the outside and inside terms will end up canceling out. And that's all there is to factoring using the difference of squares. Alright, here are 4 problems to try to factor. They're all using the difference of squares, so pause the video, try them out, and then check your answers. Alright, time to reveal the results. And here are your results. Going forward, you don't always have to write it in the format of what exactly is being squared. I've just included this here to help show you the steps that you need in order to factor it, but those are the correctly factored forms of your original polynomials. Piece of cake! Now let's take a look at some perfect square trinomials. If I have a polynomial, I can look to see if it's a perfect square trinomial because that might allow me to factor easily rather than trying out a lot of different options for things. So I want to see if these trinomials are in the format on the left sides of these equations. A squared plus 2ab plus b squared, or a squared minus 2ab plus b squared. So I'm going to look at these kind of the same way that I did with the difference of squares. I know that I could write n squared as n to the second power. And I know that I could actually, I'm going to leave a little bit of space right now, I'm going to write the 16 as a 4 squared. And now I just want to see if I could write the 8n in the form of 2ab. Since I already have it as a plus, is this true if I do 2 times n times 4? The n and the 4 coming from the first and last things that are being squared. Is that true? Is this statement the same as the previous one? And it is. N squared is n squared. 2 times n times 4 is 8n, and 4 squared is 16. So because it's in this setup, I can immediately jump to this factored form of it, which is going to be n plus 4 to the second power. And that's my factored form. It's n plus 4 squared, which I know is n plus 4 times n plus 4. So you could write it out like this as well. And if you had just factored this the normal way, you would have tried to figure out what the two numbers were that multiplied to 16 and added up to 8, and you'd get positive 4 and positive 4 there. So you could end up with the same answer doing it the traditional way. This is just a nice little shortcut. Same thing for the next problem. I noticed that 4x squared could be written as 2x, and raise that to the second power. I have a subtraction, but I'm going to leave some space. And 9 can be written as 3 squared. Now I just check. If I take a 2, and it's always a 2, and then take the 2x from the front and the 3 from the back, does that expression match my original one? It does. 2x times itself is 4x squared. Negative 2 times 2x times 3 is negative 12x, and 3 squared is 9. So because this is in the format that matches my second perfect square trinomial, I can immediately write it in the form 2x minus 3 squared. And just like the previous problem, you could write that out in an expanded form where you have 2x minus 3 times 2x minus 3. You could use the Punnett square method or guess and check in order to figure out that 2x minus 3 times 2x minus 3 were the factors of my polynomial 4x squared minus 12x plus 9. But there's different ways to multiply to 4 and to 9, so it ends up being a lot of work if we're not lucky. So if you end up having a situation where you just check quickly, see if the end pieces are perfect squares, then see, you know what, this might actually work. And if that's going to be a perfect square, then you might as well check to see if it's going to be a shortcut we can use. Alright, here are 3 perfect square trinomials. Try them, pause the video, try them out now, and then check your work. Time to reveal the answers. Alright, so here are your 3 results. The first one factors into m minus 1, the quantity squared. Second one is d minus 5, the quantity squared. And the third one, I have a hunch that some of you forgot to take out the common factor of 9 first. If you take out the common factor of 9 first, which you should always look for a GCF first, you end up getting 9 times z plus 2 squared. Now if you didn't take it out first, what you would have ended up with is 3z plus 6 squared, which is valid. However, it's actually not fully factored because the 3z and the 6 have a common factor of 3. The tricky part here is that this factor is repeated. It's 3z plus 6 times 3z plus 6. So you actually have 2 binomials with a common each with a common factor of 3. So you'd really be taking 3 out twice in order to get back to the 9 times z plus 2 squared. So you take a 3 out of the first binomial, 3 out of the second one, 3 times 3 is 9, and when you factor the 3 out of 3z plus 6, you end up getting z plus 2 remaining on the inside, and you still square that. So, hope that is clear. And that's how you can use perfect square trinomials to quickly factor. Let's just take a second to answer the question, but when am I going to use this? Well, as you know, for the most part, that's not the point of what we do. We do this because it's an opportunity to learn how to problem solve, how to persevere through difficult problems, and how to apply logical rules based on the material presented to us. So that's normally the case, but there are a couple of things that we can use this for, mostly just tricks. The first one, 54 squared minus 48 squared. If I have a calculator, sure, that's a piece of cake. If I don't have a calculator, it's a little bit more challenging. So what I could do is I could use a special product to help me with the mental math. I have something squared minus something squared, so I'm going to rewrite this as a difference of squares. I'm going to rewrite this as 54 plus 48 times 54 minus 48. And now these things actually combine fairly easily. 54 plus 48 is 102. And 54 minus 48 is 6. 102 times 6 is 612. Really no strain on the brain right there. Able to do that calculation. A calculator will confirm that that's the same value you get if you input 54 squared minus 48 squared. So that's one application. Another one is sometimes this can be used to help us solve equations quickly. If I look at the equation on the right here, x squared plus 2/3 x plus 1/9 equals 0. First thing I see is fractions. I don't like it. It's a pain. So one thing I can do is I can clear out the fractions by multiplying by the least common multiple of the denominators, which in this case would be 9. So I'm going to multiply both sides of my equation. And keep in mind, you have to have an equation in order to do this. If you just have a polynomial that factors, it doesn't work. I can multiply by 9 because I'm also going to multiply the other side of the equation by 9. Now, when I distribute that 9 to the x squared, the 2/3 x, and the 1/9, I got to remember how to multiply fractions. First one is easy because that's just 9x squared. Then 9 times 2/3, I do the 9 times the 2, which is 18, and 18 divided by 3, because that's my denominator, is 6. So I have plus 6x. And then 9 times 1/9 is 9 times 1, which is 9, divided by 9 goes back to 1. The right side of the equation stays as 0. Now I see that I would have to factor this. But I check first and I recognize that this is actually something that can be written in the format of a perfect square trinomial. You can see that if I make my a 3x and my b 1, that I'm going to have a perfect square trinomial where I could factor this as 3x plus 1 squared equals 0. Now what's nice about this is I need to split and solve, but it's the same thing. 3x plus 1 and 3x plus 1 are identical, so I only actually have to solve it once. 3x plus 1 equals 0, which some quick arithmetic and algebra will give us that x equals negative 1/3. And so that's a quick way to solve the equation. It would actually be pretty complicated if I didn't have a perfect square trinomial. I'd have to try a lot of different things, and then I maybe would have two answers. In this case, it works out rather nicely. So those are two applications of these special products. Alright, let's take a look at one last application, a word problem. A bird picks up a golf ball and drops it while flying. The function, written here, y equals 81 minus 16t squared, represents the height y in feet of the golf ball t seconds after it is dropped. The ball hits the top of a 32-foot tall pine tree. After how many seconds does the ball hit the tree? So the bird picks up the golf ball, flies it up in the air, drops the ball, and the timer starts. Timer stops as soon as it hits the top of a 32-foot tall tree. We want to know how long that took. So what we do is we use the function that's given, y equals 81 minus 16t squared. And because y represents the height of the ball at a certain time, we want to know what time it is when the ball has hit the top of this 32-foot tree. So I can replace my y, my height, with 32. Now I have a polynomial equation that needs to be solved. I'll move everything to one side so that I can have 0 in play, and that will allow me to use the zero product property, hopefully. Subtracting 32, I get 0 equals 49 minus 16t squared. When I go to factor this, hopefully what I notice is that it's actually a difference of squares, because 49 is just 7 squared, and 16t is just 4t squared. Using my shortcut, this allows me to jump immediately to 7 plus 4t times 7 minus 4t. And now I can split and solve pretty easily. I get 7 plus 4t equals 0, and 7 minus 4t equals 0. Now, if I solve the left equation first, I end up getting that t equals negative 7/4. And since we're measuring time, that doesn't make any sense. It doesn't make any sense to have a negative time. So I'm actually going to disregard that answer right away. If I solve the other equation, I end up getting that t equals -7 over -4, which would just equal 7/4, or if you prefer, 1.75 seconds. And that's the answer that I'm looking for. It takes just under 2 seconds for the bird to drop the ball and have it land at the top of the pine tree. And there you go. We used a special product in order to factor this easily and solve this problem.